extra thermodynamic advantage to evacuation. I've got one someplace here that is doubly chelated, which is even higher, and so on. Anyway, I don't want to say too much about that. Okay, so in my initial introduction, I talked about SN2 substitution of a lithium reagent, and I'd like to address that issue for a few minutes here. When you try to do SN2 substitution of reagents, you often have difficulty. These reactions don't always work well, there's side reactions, and if you ask yourself, why is that? The answer is that there's sort of complicated things that have to go on here. If you imagine, perhaps the simplest scenario, a normal sort of monomeric contact ion pair reacting with a substrate in an SN2 sense. Remember, SN2 reactions have a very, very high preference for backside attack, which means that when you do the substitution, you end up with the lithium and the anion separated by the product. This is something that Donald Cram, my PhD mentor, sort of coined a term for in product-separated ion pairs, one of these things. And he designed very elegant experiments that showed that this was a real effect, that in some circumstances, when you make an anion and the cation anion are separated by the product, it changes the chemistry. It takes a while for these two to find each other. There's an energetic penalty you have to pay because, of course, the X minus is not the sulfated by the lithium, so there's a cost to pay here. And then, of course, these things will combine and you'll end up with your inverted product. I'm not using the same R for both, okay, one's R5. Anyway, the other way that these reactions can go, which turns out to be very common, is that you first separate the ions, and polar solvents are good for this. You make a separated ion, and now you don't have this problem. Now the R minus, the carbanion part, can attack the carbon, and the lithium can assist the departure of the X group, and you don't have this ion separation problem anymore. Not only that, of course, the separated ion is much more reactive than a contact ion pair, and there really haven't been any good numbers for this until we did our work. So we have numbers that run from 10 to the 6 to 10 to the 8 reactivity difference between the contact ion pair and separate ion pair. This is a huge effect. And so it turns out that in many of the SN2 substitutions we've studied, they actually go by this pathway, even though the separation of the carbon bonds is quite difficult. So here's just sort of some experiments that kind of point the way. We looked at simply the reaction of these various lithium reagents, the rate of reaction with, say, methyl iodide in this case. And you might remember that it's progressively harder to separate the lithium from the carbon as we have chelated groups. And it turns out that the reactivity of these species goes down quite dramatically towards methyl iodide. In fact, this chelated structure is 1/17,000th as reactive as the parent system at the bottom here. And we ascribe this to the fact that probably it is the separating ion that's doing all the reaction. And for this species, there's just very, very much less separated ion present, and so the reactivity goes way down. And you would say, well, okay, you changed the structure of the lithium reagent, maybe that's the effect here. But it turns out in this series, we actually did that. If we do the reaction in the presence of HMPA, the ions are already separated, and it turns out the reactivity is almost the same for the separated ion. This is all the hand waving here, but I just expect here to show that the chelated structure is all contact, almost all contact, and under the same conditions, whereas the unchelated structure is almost all separated under these conditions. Now, we've done a lot more experiments here to sort of track this all down. It turns out if you do competition experiments, for example, between methyl iodide and ethyl iodide, that ratio doesn't change in this process, suggesting that it's the same species doing the chemistry all the time, and so on. Okay, so we did some little more complicated things as well, and we were particularly interested in the reaction of oxides with lithium because they're very commonly used as a synthetic tool. And here we got a real surprise. So here's three lithium reagents that sort of span the range of, let's say, carbon-lithium contacts. This one here, actually I should draw that as separated. This one is a separated ion PHF, in other words, it's not bonded to carbon. That's because these pentyl groups or the trimethyl groups really stabilize the negative charge, and it sort of was careful. Here's a compound that we call a weak ion pair. You add a little bit of HMPA to this, and it falls apart. Here's lithium, very, very commonly used lithium species by synthetic chemists. It's a strong contact ion pair. You have to have a number of codes of HMK before you pull the lithium off that, but you can't pull it. And so we looked at the reactivity of these three species with two typical electrophiles, types of electrophiles. So alkyl halides and oxides. And you were looking at this and say, well, there's something really complicated going on here, right? Because there's very different behavior for these three types of species. So let's first look at the strong contact ion pair. In THF, it's 99.99 something percent contact ion pair, but as you add HMK, you get more and more separate ion pair, and as you might expect, the reactivity goes a lot. In fact, goes up by a factor of 5 million between THF and HMK. And we think that is really entirely due to the fact that we're making 5 million times as much separated ion pair, and so the reactivity goes up by that amount. So that's behavior there. So why does the epoxide go up only almost half that much on a log scale? So this is a factor of 8,000 only. And the answer to that is that in addition to making more separated ion when we add HMK, we're also destroying the ability of the lithium to behave as a catalyst for the opening. In other words, oxygen that's formed, O-, is a pretty basic site, and it helps a lot to have the lithium sitting on the oxygen. And so this gap here is sort of a measure of the effect of lithium catalysis on the epoxide opening. So this is the rate of the increase to separate ion and the reduction due to loss of catalysis. Now, the separate ion pair shows the expected behavior then. So the iodide, you add HMK to it, the rate doesn't change at all, no effect at all. Why is that? Well, iodide doesn't need a lithium to help it move. Iodide is perfectly happy without any contact. In fact, the THF iodine is ion pair, it's not contact. The epoxide, on the other hand, simply the reactivity goes down eventually to about 1/4,000 as fast, because what we're doing here is we already have all the nucleophilicity, but we're reducing the electrophilic behavior. So HMK can either destroy a reaction in that case, or it can greatly accelerate it in this case. So you have to know what's going on in these things before you do this. There is some literature, people who have battled with this problem without knowing what's going on. The intermediate one shows intermediate behavior. The halide goes up modestly by about a factor of 300. The epoxide goes up a little bit and then it goes down, because these two effects are now really matched. And initially you get the one effect and then the other one takes over. And that illustrates. So for this phenylthiomethyl lithium, we did a whole bunch of different alkyl halides, and all of them show exactly the same rate increase when you add HMK. And that simply tells me that what we're doing here is THF, we have 1/300th of a separate ion pair, and that does the chemistry. Then we add HMK, we get 100% ion pair, the rate goes up by a factor of 300. And it doesn't matter whether it's an unreactive halide or a very reactive halide, you get the same effect for all of these. So the indication is that the contact ion pair does none of the chemistry here, and all of the chemistry is done by a separated ion pair, and that's the only way to explain all this kind of information. Okay. Diphyne, I've already gone through the process. We've done a lot of experiments with diphyne, and here also, everything we tell says that this species is unreactive. It doesn't do any alkylation chemistry with oxides or with alkyl halides. All of the chemistry goes through this, and the best number we have is that the separate ion pair is about 140 million times as reactive. At least it's 140 million times as reactive as the contact ion pair. There's no lithium catalyst for chlorine or the iodine leaving, but if you have fluoride as a leaving group, then you get catalysis. Of course, fluoride being much more basic, it helps to have the lithium there. And of course, with epoxides, you get this reduction because of the So I won't belabor this. I've already gone through the process. So we have two competing factors here. The lithium catalysis would go up like this, but it starts that way, but then you lose catalysis, and eventually you go to the uncatalyzed process, which is this right here. So there's two competing processes which are kind of merging to get this result. THF to get the fully catalyzed process, and HFT to get the uncatalyzed process. Okay, so there's some starting in here eventually. Something else? Another lecture?
We have it till 2:30.
To 2:30.
We have the room.
Well, I hope not to take that long, but I still have some things I want to tell you. So in case you're thinking about what I'm telling you, is that you're saying, well, this guy's giving us a lot of circumstantial evidence here for these intermediates. Well, hand wave here, hand wave there, so on. And you're right. I mean, with lots of science is circumstantial in nature, we just build up a strong circumstantial case in many things. It is nicer, however, to get more direct evidence. Now, the reason that this is all circumstantial so far is because of the Curtin-Hammett principle, which I'm sure you covered at some length. So the Curtin-Hammett principle says that if you have two species, in our case it's these various lithium species, that are in rapid equilibration, then very often you cannot tell who did the chemistry because the rate of reactions are much slower than the rate of interconversion, and so there's the products give you no information about which one of these things did the chemistry because they're in equilibrium, and either one could be doing it, or one could be doing all of it. The case I've shown you, it looks like the separated ion pair is doing all of the chemistry, even though what you see in solution is the contact ion pair, in fact, to a very, very high extent. And this goes for these other species as well: dimers, monomers, pentamers, dimers, mixed aggregates, various solvates, and so on. All of these things are in relatively rapid equilibrium. And if you want to do kinetic studies, for example, you have to have a reaction that whose rate you can actually measure, which means for classical kinetics, it has to have a half-life of, let's say, at least a minute or two to sample it in any kind of a reasonable way. And so people choose reactions. In fact, the lithium reagents, they choose often bizarre reactions that are slow enough that you can measure the rate, because most of the reactions that people actually run, the rates are way too fast to measure by normal techniques. And so we're usually in a situation where we've picked a bad reaction because we can measure it, and we're trying to learn about these things, but we can't because of the Curtin-Hammett principle. Okay, so to give you an idea of what these barriers are like, if you have a half-life of 60 seconds, which would be very fast for a classical kinetic study, and you're working at minus 78 degrees, the free energy of activation would be about 13 kilocalories. So that's what the barriers are like for the fastest one that you can study. For more comfortable kinetic studies, you need barriers of 15, 16, 18, 20 kilocalories, and then these things become sort of doable with sampling techniques of 1 kilopascal. So the question is, can we find reactions that are actually faster than this interconversion? If we can, then we can study these species independently as reactive species. Right? So this is what we call defeating the Curtin-Hammett principle. Right? So the way you can't change these barriers except by changing molecules, changing structures, and so on. But you can change these barriers by choosing the right substrate for your chemistry. So that's what we set out to do. So what are these barriers for interconversion like? Here are a bunch of systems that we studied, and you can see what the barriers are like here. This lithium reagent here is going to feature a little bit in our system because it turns out we have some of the highest barriers of all of these kind of interconversions. So this contact-separated ion pair interconversion has a barrier of 9 kilocalories per mole. Just to give you a preview here, we will eventually be able to measure things at about 8.5 kilocalories per mole. So this is just getting to the point where we might be able to independently look at the reactivity of these two species. Okay, it's very close, but it can be done. The same species forms a triple ion, and that triple ion has a barrier of 16 kilocalories. Now, 16 kilocalories gives you a lifetime of like days at minus 78 degrees. So there's a species that we can study at length. We can do classical kinetics in that species and compare the reactivity of triple ion with these other species. So this is a good system. But most other ones, 10 lithium monomer dimer, which we've done a lot with, and I'd like to do more. 8.6 is just at the edge. But I will show you, we actually did one experiment that caught that thing, but it's very close. Many other, for example, this more typical contact ion, separated ion pair has a barrier of 5 kilocalories. It is beyond any classical kinetic technique. This would require, some physical chemists to do this. Organic chemists can't work on time scale of microseconds. Here's a tetramer dimer. This is also a very favorable one. This is butyllithium. Butyllithium PHF is a mixture of dimer and tetramer. You can see both species. The barrier is 10 kilocalories per mole. This is pretty comfortable, and I will show you that we can study those species independently using this technique. So that's kind of where we stand. So I hesitate about this graph. horribly complicated. But this is sort of the current habit limitations on a delta G scale. So let me explain what we're talking about here. So this is a graph of temperature, because one of the ways that you can slow down reactions is by lowering the temperature. Okay, so we're going to be doing that. And we have then these graphs. This is the free energy of activation at this point. So the interconversion of these species has a line, temperature dependence. For example, this triple ion, whose barrier is 14 kilocalories, this is the barrier to interconversion of these two species. If your rate of reaction is above this, then you're working under current habit conditions. Current habit implies you cannot tell who's doing the chemistry, okay? If you're below this line, if you're below this line, if your reaction has activation energy below this line, then you can study the two species independently. Okay, so that's what this graph is explaining. Now, of course, you have a time scale for observation, which are these lines over here. So this is the time scale for a half-life of 15 seconds. You're going to have to be above this in order to measure anything under that time scale. Below that, it becomes unmeasurable. Here's a time scale of 1 second. So if you work on a time scale of 1 second, then you can measure everything in here. So the area between this line and these lines is the area where you can do successful kinetic experiments. Okay? Below that line, the reaction is too fast. Above this line, you work under current conditions. Got it? Okay, everybody's done. All right, so different species have their limitations. For example, here's the butyllithium tetradimer. Here's the line. So you have to go to at least minus 105 before you even have a prayer of doing a separate reaction with a time scale of 15 seconds. With a time scale of 1 second, you see you can operate at minus 85. But if you can operate at minus 145, you see you've got quite a range where you can work with butyllithium dimer and tetramer as independent species. You can do one, you can do the other, you can do something. Okay, here's the contact ion separate ion pair of that crystal lithium, and here's phenolithium dimer monomer, and here's the sweet spot for those. So if you work on a time scale of 1 second, you've got this little tiny area. If you can pop an experiment in there, you learn something about what the monomer does versus what the dimer does. So that's the stage. How are we going to do this? Well, I was going to bring the device here because it's around here somewhere. We built a rapid injection apparatus for NMR spectroscopy. So this is an apparatus that you strap to the top of an NMR spectrometer. It has a mechanical stir that runs right down into your tube. It has two injectors, two syringe injectors that also run down into your tube. So you can do two sequential reactions in one pot. And the whole thing is controlled by the spectrometer. So basically, once you have this thing set up, you put your substrate in your tube, you cool it down, you set all this stuff up, and you go to NMR spectrometer, you say start, and the thing injects one thing and starts making NMR spectra. Now we can quite easily take spectra every quarter second. Okay, that's kind of our time scale. More realistically, it's a sort of a 1 second time scale, but that's pretty comfortable for this experiment. So mixing actually takes around 3/4 of a second, typically, because we have to stir the thing for a while. And the NMR spectrum look really shitty when you're stirring at the same time. So after we finish stirring, we raise the stir, and then we get a nice clean NMR spectrum. So let's say the first second is dead time, and after that we can measure spectra every quarter second, or whatever, however fast we want. So this is the rapid inject NMR apparatus. This is a pretty low-tech device. I think it costs us about $800 for the parts to build this thing. The key part was to hook this up to the spectrometer, to make the spectrometer actuate these very valves in the injectors. Charlie Fry and his team there did all of that for us. This is the first rapid injector that was built. There was a very old apparatus that was done a long time ago. And it was built on a different principle. Basically, what they did is they had a syringe that sort of went down the inside of the probe right into the NMR tube. And they were able to get a shorter time scale than with our wake up. They were able to get down to a tenth of a second. But the problem was that they mixed by injection. In other words, the whole point was you did a really, actually hit the thing with a hammer, essentially, to inject so hard that it mixed the thing, and then you could take an NMR spectrum. But this created a viscosity problem, so that I have never seen any experiments below, I think, minus 85 with this experiment. And as you can see, minus 85 from that earlier graph. For example, with butyllithium at minus 85, So you're really on the edge of being able to do any useful experiments. In fact, Garrity measured the relative reactivity of deuterated tetramer and dimer with this apparatus towards some deprotonation reactions. He found a number of 10. We have measured the same number and we get 10 to the fifth. Okay, so he was wrong. He was too close to the limit of his effort. All right. So we can do these kinds of experiments. Here's a good lithium experiment, just to give you an idea of what these things look like. The NMR spectrum is pretty. We're looking at lithium NMR. Lithium NMR is very effective for this kind of experiment. Ooh, I'm running low. Okay. It's very effective for this kind of experiment because the relaxation time is very short.
This is their final exam, so.
That's it. So the relaxation time is very short, so you can really do quarter-second experiments. Here's in THF butyllithium. So we have here the monomer and here the dimer, you see two peaks, and we inject into this solution trimethylsiloxane. We're just simply going to do deprotonation at this proton here. And you can see the dimer goes away. Let's see, by 1.5 seconds, the dimer has all reacted with the acetylene. It's gone. The tetramer sits here, and finally starts to go away at, 8,000 seconds, 11,000 seconds. And it turns out that going away here is actually not a reaction of the tetramer. What's happening is the tetramer is dissociating to the dimer, and then it reacts. And the reason we know that is you can squirt in as much acetylene as you want, but the latter part of this rate is always the same, and so it means it's 0 order per second. So this is actually the acetylene, the tetramer does not react at all. So you can see just looking at this that there's a big difference in rate, and it's many parts per K. We get pretty decent kinetics from these kinds of experiments. So here is what's going on here. The dimer disappears. The mixed aggregate between here's the butyllithium and the acetylene. Remember, I talked when you're doing a reaction like this, there's always going to be mixed aggregates. Here's the mixed aggregate building up, which is also reactive and goes away. And here's the final product, the homodimer of the acetylene building up. And here's the tetramer just sitting here. This is a 30-second time scale. And you can see that's a comfortable kinetic experiment. 30 seconds is great for this. Where I was having a week looking over. To have the tetramer go, we have to watch it for hours, and it slowly goes away. As I said, it's 0 order instead of the tetramer is not reacting, it's just dissociating. So here's some numbers that we gathered from this kind of experiment. And this was a few years ago, but these were the first numbers of any kind that were reliable about reactivity of any of these species. It simply wasn't known before. So dimer and tetramer. This acetylene protein, here's a different acetylene, and we did various ones, but we eventually ended up being able to find an acetylene that did react with the tetramer. We had to go to the somewhat more acidic acetylene. We did some extrapolations, and we decided that it was about a power of 10 to the 8 difference in reactivity between the dimer and the tetramer. Remember, the best previous estimate was 10. Okay, so this I think is. It's not what you might call a solid number, but it is good probably to at least an order of magnitude, maybe a little bit better than that. But anyway, these are such large numbers that that's the So the difference in aggregate reactivity is enormous. And remember, the monomer is probably going to be again that much more reactive, and the separate ion again that much more. So we have a huge reactivity. Mixed aggregate, we can even measure the reactivity of the mixed aggregate versus the homo aggregate. The homo aggregate is about 40 times as reactive as the mixed aggregate. And this is not surprising because this is a weaker donor to the lithium, which means the lithium solvates the butyl better, and that makes its reactivity lower. So it's a very logical relation. It's only a factor of 40, but that's what's going on in the solution. Now, of course, we don't just calculate, don't just deprotonate butyllithium, we can also add to electrophiles. We looked at aldehyde, we can get about a factor of the fourth. The dimer is gone faster than we can measure it. The tetramer is a measurable rate, so we get a number of about 10,000 for reactivity between these two. The actual number is probably much lower than the well-based numbers. Because of dynamic range problems, we cannot do all of it. And we found one lithium reagent, this thing with sort of an unusual structure to it, which is present in THF solution as a mixture of tetramer and monomer. Very unusual kind of situation. And here we're able to compare the reactivity of tetramer and monomer. We found 10 to the 15th, which is kind of, equivalent to having some of these happen twice. So these are real numbers. Here's another surprise. At this stage of the project, any experiment we did was the first of its kind on Earth, right? I mean, nobody's ever been able to look at these kinds of things before. So we looked at a whole bunch of different electrophiles with lithium diamond. These are different electrophiles. We got a little surprise here. So here's a lithium diamond reacting with methyl benzylate. It has a convenient rate. Half-life is about 24 seconds. If you do acetone, it's quite a lot faster. Everybody knows, ketones are more active than esters towards lithium dimer. But here's an amide. The amide is more reactive than the ketone. Okay? Now that's a surprise. That's not what you teach your Chem 345 students. Because in almost all circumstances, amides are less reactive. By circumstances, we mean hydrolysis with hydroxide and water. Okay? Amides are many powers of 10 less reactive than esters in an hydrolysis reaction. And that's why living organisms use polypeptides, not polyesters, for all their stuff, because of how they hydrolyze. So I actually spent quite a bit of taxpayer money to try and track that problem down. I can't say I really understand what is going on there. Believe me, we tried hard. Almost burned out a student, I think, and a half. But it clearly must have to do something with the basicity of the system. So Lewis acid catalysis by lithium becomes a very important feature of these reactions, enough to kind of turn these normal reactivities upside down. Anyway, so that was a little surprise there. I won't talk too much about that. We did look at these reactions more carefully. Here's a phenolithium. We're doing ferrofluoro. Eventually, I got smart and I had my students put fluorine on everything. And then we can use fluorine particle stuff, and it is beautiful. I can recommend when you do your research, you want to follow something, think about sticking to fluorine something, because it is beautiful. No interference from solvent, high sensitivity, in our case, relatively low capacity oxidation. So here's phenolithium dimer and monomer reacting with ethyl benzene. Okay, let's see what's going on here. The first thing we see, if you look at the NMR spectrum, is a 1-to-1 triplet in the fluorine NMR spectrum, and we can assign this quite securely to this structure here. This is a mixed dimer between phenolithium and the tetrahedral intermediate of an ester. My knowledge, this is the first time anybody's seen a tetrahedral intermediate actually in these reactions, which we know are always there. But here it is. It's stable at minus 90 degrees for hours. It starts to decompose if you warm up above minus 90 degrees. The three fluorides, of course, the three peaks are these three fluorides. These and this one are also different, and they show up there. If you allow this reaction to continue, then the other part of this reacts to give the homodimer of the. And then if you watch longer, this thing slowly falls apart. You get the ketone, and if there's lithium reagent left at that point, you get the addition of ketones. So all this works out very well. So this is interesting because if the monomer was doing the chemistry, you might expect that what you would see is the monomer of the tetrahedral penta. Can't you see the dimer? And so this is another thing that we put a lot of effort into trying to understand. We eventually decided that the monomer was being formed, but it was grabbing the phenolithium very quickly, forming this dimer because the monomeric alkoxide is really, really unhappy and is looking for other ways to stabilize itself. So that's the story with the esters. So here's the experiment that we did on ketone. We tried to look at phenolithium monomer dimer mixture reacting with esters. We could not find an ester that was fast enough to fall in this little spot here that I mentioned earlier. In other words, the reactions are too slow for this. We said, well, let's do a ketone. Maybe a ketone is fast enough. And sure enough, it is. So here's the monomer dimer line for hammer business, and we have to do an experiment in this region with our 1 second time experiment in order to distinguish reactivity. And here's that experiment. Now, the truth in advertising, we did probably about a dozen of these experiments. About seven of them didn't work for one reason or another, but this is one of the ones that did. Now, you know, when you publish stuff, you don't show the other ones. So what happens here, what happens at this temperature is that you get gelling, you get PHF crystallized out of solution, you get a lot of feeds, you get strange things happening. But this is one of the ones that work. So we're looking at thorium and Oregon here, we're looking at this thorium. Here's the dimer, and here's the monomer peaks of the starting material. There's some other stuff in here that I won't talk about. But we inject ketone, and 1.4 seconds later, you can see that the monomer is gone, and the dimer is still there. Okay, so this is a sort of non-trivial. So we can say that the monomer is also more reactive than dimer in this case, which is no big surprise actually. But this shows that that is in fact the case. A couple seconds later, the dimer is also gone, so it's reacting very quickly. But presumably it's reacting by dissociating the monomer and the monomer. Okay. Well, I don't know if I should spend. That was a kind of interesting thing. So here's this lithium. I mentioned this lithium. We call this crystal lithium, trimethyl lithium. Very unusual lithium base, extraordinarily sterically hindered, and this gives it somewhat unusual properties and desirable properties from our point of view. So the NMR spectra show that this species in THF is a mixture of three species. There's the contact ion pair, there's the separate ion pair, and there's the triple ion, and all of them are populated, which is really quite unusual in this business. Usually you just see two. We have a couple species with three present. This one has three present, and it's three such different structures. And the barriers to conversion are quite high. Here's the evidence. So we made the carbon-13 labeled compound. Here's the triple ion, a lithium coupled to two carbons. Okay, that's a triple ion. A lithium coupled to one carbon, that's the contact ion pair. And then we have a lithium which is coupled to a carbon that's coupled to no lithium, and that's a separate ion pair. That's not all the evidence. We have lots of information about this. And here's the barrier to conversion. At low temperature, we have three species, and then two of them coalesce, and then the other two coalesce. We can get the barriers from that. So here's the current dynamic picture for this system. Here's the triple ion conversion, very high, lots of dynamic range to work with here. And here's the contact ion separate ion pair, kind of a little region where you might do an experiment. But this barrier is pretty low here. So this is about 8 kilocalories or so in this, 9 kilocalories, 16 for the other one. So these are three species that we can, in principle, study independently. So there's some strange stuff that goes on here. So here, for example, is a reaction of the triple ion. We do a very simple experiment here. We make a solution of this that has a bunch of triple ion, has a bunch of the other stuff. We inject some methyl iodide. This immediately uses up all the other ones. Triple ion doesn't react with methyl iodide. Then we can add aldehyde to this thing to the triple ion to its chemistry. So we have this kind of a purge system. So we're looking at the aldehyde reaction with